Right now, as you're reading this, there is a process happening inside your Nissan Z, your Infiniti Q50, or your Q60 that Nissan's own engineers documented internally and then buried. Your turbos are spinning at over 200,000 revolutions per minute, and the single most critical thing keeping them alive is a column of pressurized oil thinner than a drinking straw. And that oil passage, that microscopic lifeline, was deliberately sized in a way that makes catastrophic failure not a possibility, but a statistical certainty over time. Nissan knows this. Their service network knows this, and every single time a VR30DD-TT owner walks into a dealership with a destroyed turbocharger, those service advisors smile, quote you somewhere between $4,000 and $9,000, depending on whether it's one turbo or both, and they never once mention that the root cause was baked into the design before the car ever left the factory. I am going to destroy that business model today. I am going to take you inside the fluid dynamics of that oil feed circuit, into the metallurgy of that turbine shaft, into the electronic logic of the turbine speed sensors, and I am going to show you exactly why this engine eats turbos, and more importantly, exactly what you can do for under $100 to stop it forever. The industry is not going to like this video, but you need to watch every single second of it. To understand why the VR30DD-TT fails, you need to understand what a turbocharger actually is at the physics level, because Nissan's engineers certainly did. A turbocharger is not just a fan bolted to your exhaust. It is a precision rotor system operating at thermal and mechanical extremes that most people cannot even conceptualize. The turbine wheel on the hot side of your VR30's twin turbos sits inside a housing where exhaust gases routinely exceed 900 degrees Celsius. That wheel is typically cast from a nickel-based superalloy, sometimes a Mar-M or Inconel variant, chosen specifically because these materials maintain their tensile strength even when glowing near their melting point. The compressor wheel on the cold side of your VR30's twin turbos is typically a high silicon aluminum alloy, lighter and optimized for thermal cycling. These two wheels are connected by a shaft, usually forged from a hardened martensitic stainless steel, and the entire assembly floats inside a center housing on nothing but a thin hydrodynamic film of engine oil. That word, hydrodynamic, is everything. The turbine shaft does not touch the bearing surfaces when the system is working correctly. It floats. Oil is pumped under pressure into the center housing, and as the shaft spins, it creates a self-sustaining wedge of pressurized oil between the journal bearing and the shaft journal. The shaft is literally riding on a wave of fluid. This is the same principle that allows massive industrial turbines to run for decades without significant wear. When the hydrodynamic film is intact, bearing wear is virtually zero. When that film collapses, even for a fraction of a second, you have metal-to-metal contact at over 200,000 RPM, and the resulting friction generates enough heat to weld the shaft to the bearing in milliseconds. That is what turbo seizure is at the physical level. It is a catastrophic film collapse event. Now here is where Nissan made a choice. The VR30DD-TT oil feed lines going into the turbocharger center housings on both the driver side and passenger side turbos are fed through orifices that the factory calibrated for what Nissan internally describes as adequate lubrication under normal operating parameters. And that phrase, normal operating parameters, is doing an enormous amount of work. Because here is the truth of fluid dynamics that any hydraulic engineer will confirm. Oil flow through a restriction orifice is governed by the Hagen-Poiseuille equation. Flow rate scales with the fourth power of the radius of that orifice. This means that if you reduce the orifice diameter by even 20%, you do not lose 20% of your oil flow. You lose roughly 59% of your oil flow. The relationship is brutally nonlinear. The factory orifices on the VR30 DDTT have been measured by independent shops and documented within the tuning and motorsport community at approximately 0.7 to 0.8 millimeters in effective internal diameter. At factory boost pressures with clean, fresh, low-viscosity oil at full operating temperature, this is borderline adequate. The hydrodynamic film survives. But now introduce two real-world variables that Nissan's engineers either did not properly account for or chose to minimize for cost reasons. First, oil coking. At the temperatures inside a turbocharger center housing, particularly after a heat soak event when you shut the engine off and residual heat bakes the oil sitting in those passages, oil does not just drain away cleanly, it carbonizes. It leaves behind a lacquer-like deposit on the internal surfaces. Over thousands of heat cycles, these deposits accumulate inside those already narrow feed orifices. An orifice that started at 0.75 millimeters of effective flow diameter might functionally drop to 0.6 millimeters or below after 2 or 3 years of normal driving. Apply the Hagen-Poiseuille relationship, and your oil flow to the turbo bearings has potentially been cut nearly in half from what the factory calibrated as minimally adequate. Your hydrodynamic film is now living on a knife's edge. The second variable is turbine speed, and this is where the story gets darker because it pulls in the electronic side of this failure mode. The VR30 DDTT is managed by a sophisticated engine control unit that monitors boost pressure from the compressor outlets and uses weight gate control to regulate how hard the turbochargers are being pushed. But the system also relies on turbine speed sensor signals to understand the actual rotational state of the turbine wheel. Here is the critical flaw in the calibration logic. The factory ECU has a turbine overspeed protection threshold, but that threshold was calibrated with the assumption of an intact, leak-free intake tract. When you have a boost leak, even a minor one, perhaps a cracked intercooler coupler or a loose charge pipe clamp, you get a pressure differential anomaly. The compressor outlet pressure drops. The ECU reads this as insufficient boost and commands the weight gate to close further, driving more exhaust energy into the turbine. But the actual turbine speed is not being directly measured in real time with sufficient resolution to catch a developing overspin event before it exceeds the structural limits of the compressor wheel. The compressor wheel on a turbocharger has a specific design speed limit. Beyond that limit, the aerodynamic loading on the wheel's inducer blades encounters localized aerodynamic loading that exceeds the material's fatigue endurance limit. Aluminum alloy compressor wheels are particularly vulnerable to this because aluminum does not have a true fatigue endurance limit the way ferrous metals do. Every cycle of stress, no matter how small, contributes to fatigue crack initiation at the blade root. When the ECU is simultaneously starving the bearing of oil through a coked orifice and driving the turbine into overspin territory through a miscalibrated boost response to a leak condition, you have created a perfect storm. The bearing film collapses from inadequate oil delivery. Friction at the journal generates heat that migrates into the compressor wheel hub, and a wheel that was already aerodynamically overstressed now has a thermally weakened hub. The result can be a catastrophic wheel failure, where compressor blade fragments exit the turbocharger housing at velocities sufficient to destroy the intercooler, the intake manifold, and anything else downstream. This is not a scenario from a track car pushed beyond its limits. This is a scenario that owners have documented on completely stock VR30 DDTT vehicles with under 60,000 miles, doing nothing more than a spirited on-ramp merge. And Nissan was aware of this failure mode. There are technical service bulletins in the Japanese domestic market documentation that acknowledge turbocharged. Right now, as you're reading this, there is a process happening inside your Nissan Z, your Infiniti Q50, or your Q60 that Nissan's own engineers documented internally and then buried. Your turbos are spinning at over 200,000 revolutions per minute, and the single most critical thing keeping them alive is a column of pressurized oil thinner than a drinking straw. And that oil passage, that microscopic lifeline, was deliberately sized in a way that makes catastrophic failure not a possibility, but a statistical certainty over time. Nissan knows this. Their service network knows this, and every single time a VR30DD-TT owner walks into a dealership with a destroyed turbocharger, those service advisors smile, quote you somewhere between $4,000 and $9,000, depending on whether it's one turbo or both, and they never once mention that the root cause was baked into the design before the car ever left the factory. I am going to destroy that business model today. I am going to take you inside the fluid dynamics of that oil feed circuit, into the metallurgy of that turbine